Welcome to the last part of the. Okay, it's without microphone. Good morning, everyone. We are ready for the last part of our Majorana Lectures. Pardon me?
We are free. There is no camera.
There is no camera. We register with
The Teams.
So
I hope
we try to give our best. Yes.
Without microphones.
No.
Go back to
Okay.
human relations.
Yes.
Okay.
So today's title is Promising, Tutti Frutti and Scattering Approaches to Binary Systems. Please say.
Before entering the details of the scattering approach, let me start by reminding, although the scattering approach, for instance, now is kind of fashionable and is giving important new results, actually it's probably reaching the end of what can be computed with the scattering approach. It has also quite disappointing aspects. So it's both extremely important conceptually, technically, like that, but still for the future, probably we will need to continue using a set of various tools which complement each other and which allow to have a good description of the two-body problem in general relativity. And among these tools, the oldest one is the post-Newtonian one, which essentially counts the powers of 1/c everywhere. So on the right-hand side of Einstein equations, you have Newton's constant always comes divided by c squared. So terms like the potential between two bodies as in dimensionless form is this. And for kind of elliptic orbits with eccentricity of order smaller than 1, by the virial theorem, v squared over c squared is of the same order numerically as this, which means if you count 1/c squared, you are good for bound states. But in the post-Newtonian method, also traditionally, in the old post-Newtonian method, you also count the 1/c's that appear in the time derivatives, okay? Which means, for instance, each time you start solving Einstein's equations, and then on the left-hand side, we have the D'Alembert operator acting on H. This is the Laplace operator minus 1/c squared dt squared of H. And when this is equal to something on the right-hand side, in post-Newtonian, actually, you put this term on the other side, okay? You don't solve this, you solve this, equal this on the right-hand side, plus a source term which contains linear term, like the stress energy tensor of matter, which are localized in delta functions. And then you have nonlinear terms from Einstein's equations, like two derivative acting on H, sometimes two derivative on the same object. But this way of simplifying things, for instance, when you do the first post-Newtonian approximation, you find that the main term which appears here comes from the fact that H00 is twice the Newtonian potential U, satisfying Poisson equation, times rho, over c squared with G. And therefore, this term contains the gradient. First, in this derivative, you keep only the space derivative. So, for instance, these terms, you have the space derivative of U contracted with the space derivative of U. Or if you have two derivatives here, you have U times the Laplace operator acting on U. So these are nonlinear terms at the lowest order on the right-hand side. But actually, it's very easy to deal with this because by this equation, this term is localized on the source, okay? So it is minus 4 pi g rho times U, localized on the source. And this term, which looks non-local gravitational energy in between the two bodies, actually, you say, I will just compute the Laplace operator acting on U squared over 2. If you do this, this is, you put one derivative inside, and then this gives U di U inside, quadratic. U expand, it gives du di U, plus U Laplace acting on U. This is local, this is non-local, but you can write it as the Laplace of U squared, and then you put it on the left-hand side and you can solve. Because of things like that, the PN expansion actually can solve things to very high order. And when you get non-trivial integrals, they are much simpler than there are integrals in 3 dimensions with quasi-static things. And actually, even if one has to use like Feynman type tricks to compute difficult integrals when you go to high PN, you can go to very high nonlinear orders, okay? But the point I want to make here is this condition that time derivatives are much smaller than space derivative actually is valid only in the near zone. That is to say, if you consider a region much smaller than the wavelength emitted by the system, because when you write this, you find omega r, okay, which is the condition that the distance at which you are is smaller than the wavelength. And therefore, the post-Newtonian method, although in the old days it was not immediately clear, is something which, when you have a two-body system, is valid only within a region much smaller than the wavelength, but not valid in the wave region, and therefore you need to complete it by other things. Okay? Now, the so this was for the post-Newtonian. A second method, which was actually used long ago, it has become fashionable again, but it's the post-Minkowskian method. By the way, when I started working on gravity, this was called the fast motion approximation. And then in some papers I said maybe it's good to have a name which is close to post-Newtonian. And as this thing says that G nu starts with the Minkowski metric, and then you start having a first order deviation, you count powers of G now, okay? G squared second OME, so it's a perturbation theory around flat space in powers of G, and you don't count the velocities. You don't care if the velocities are small or close to the velocity of light, although evidently the velocities can be small also. They say if you have a result in post-Minkowskian, you can just say, okay, let me take the limit where also velocities are small, so there is a connection between this and this, evidently, and you have many connections. So in that case, yes, let me mention something that will be a very simple thing. If I have two now word lines, okay, and I want to solve Einstein's equation, but in the right-hand side, the stress energy tensor is the stress energy generated by two word lines, which means it is a stress energy tensor, which is a sum over the two particles, let's say 1 and 2. So I have an index which takes value 1 for the mass m1 and m2, and the stress energy tensor, it is an integral over a proper time of the elementary T mu nu of one test particle is proportional to the mass, the 4 velocity tensor with itself, and it is localized on the word line, which means that I have a delta function here. It's a function of x in space-time, x, and here I have, let's say, xa as function of tau. This delta function reduces, it's a distribution which is 0 everywhere except on the word line, but all along the word line. So it's given by this formula. And then you want to solve equations of the following type. So you are going to solve, you remember h bar means h minus 1/2, etc. I have the number of h mu equal minus 16 pi g, this thing. Okay? But this is a coupled system because you cannot say I know the word lines in advance because the word line is acting on each other. Therefore, each word line will be deflected by the gravitational field of the other one, and will also include at some level self-action of the word line on itself, which means that in diagrammatic language, when you solve this field equation, in which you must add now all the nonlinear term on the right-hand side, in mathematical language, you could say you solve this by Picard perturbation theory, which means you solve you take the zeroth order motion for this, you solve for this, then you take into account the iteration, what happens thing, which means that now people draw diagrams because it's convenient to think of in terms of diagram. The linearized metric would be, I compute at point X the field generated either by the first word line or the second word line. It is the retarded propagator acting on this. And you can do this even if you assume that you don't know yet what is the motion, but you will compute the motion is a straight word line which is curved by the influence of the other. So you need to write an equation of what is the curvature of the first word line. And this is obtained by writing the equations that, by definition, the first derivative of the position is the velocity, and the derivative of the velocity, theta y, is, you can write, it's obtained by the geodesic equation, which says that each word line is actually following a geodesic in the full space-time, including the action of the word line on itself. Mathematically, it seems ill-defined because the field acting on itself is infinite, like you have a point particle acting on itself, but there are ways of proving why it is correct, various ways, and there is a technical way to deal with this, which now is used all the time, which is dim-reg, dimensional regularization. That is to say, you solve Einstein's equations not in 4 space-time dimension, but in d space-time dimension, and it gives rise to integrals which are analytically continued in d dimension, and then it gives a finite answer up to the 6th order in g, okay? For subtle reasons, okay, I don't want to enter the many subtleties, but dim-reg is a very efficient way. What I want at this stage to say is, I did not write this u alpha, u beta, a for the particle a, where this is computed at x equal xa, and then you can compute what is the deflection, okay, the change of u between minus infinity and plus infinity, or better, if I introduce P A mu, the momentum, the kinematic momentum of each particle. If you use this equation, you multiply it by ma, both sides, you integrate from minus infinity to plus infinity, you get that the change of the momentum, the form momentum, which is the deflection in space-time, now it's called the impulse, is given by an integral from minus infinity to plus infinity to d tau of this thing, in which the gamma is defined by this and contains the metric itself, which is defined by this, including this. So at the end, the deflection is given by a set of perturbation theory in powers of g. I will, a little bit later, solve for you explicitly the first order to see what kind of integrals come in. But what I want to say here is that on the right-hand side, T mu nu contains the sum of the two masses, m1 plus m2. And then, so when you solve H, you have here m1 plus m2. When you take nonlinear terms here, you will have terms quadratic bilinear in m1 and m2. When you insert in this equation, this is polynomial in m1 and m2 at each order. So at the end, you prove very easily that the impulse of each particle, when you express it in terms of incoming data at minus infinity, so you need to say, I give incoming data for scattering, saying that two particles come with some 4 velocities and some impact parameter b that I will not defined now, but in the center of mass frame, the impact parameter is coming from the incoming momenta, is the distance between the incoming asymptotic lines, okay, which exist in the center of mass frame. They are logarithmic drift in other things, but they are not important for the impact parameter. So, at the end, what you prove is that this is a polynomial in masses when it is expressed as a function of the impact parameter. And so it looks like a trivial remark, okay? I have M1, M2, M1, M2 square, and things like that. But actually it is extremely useful. It restricts things which would be very difficult to compute if you did not know it was polynomial in masses. The next approximation methods which is used, I don't need to rediscuss it because this is what I explained yesterday. This is the multipolar post-Minkowskian method, which distinguishes various regions around the system, near the system, outside. It uses multiple expansions. Yes, let me mention also something which is usually not well encoded in textbooks, because most of the textbooks either have been written before a lot of this work was done, like MTW and Weinberg, or the ones that have been written are by people who did not understand that there was new progress in the way of doing post-Newtonian theory. But so let me just mention that if you open a usual textbook and you say, what is the explicit 1pn metric and 2pn metric? You don't find the good formulas. Okay, the good formulas are the following. There is a good way of writing the 1pn metric, which is to use an exponential parametrization. Let's say -4 over c cubed, and this is plus exponential plus 2w over c squared times delta ij. That is to say, at 1pn, let me check that I did not make a mistake in writing this. Yes. If instead of saying I expand the 0,0 component of the metric as 1 plus Newtonian potential plus thing, you say, let me write it in exponential form, then you find that this W satisfies a linear equation. Actually, it satisfies D'Alembert of W is minus 4 pi g times T00 plus TSS over C squared, which is what I called sigma before. A very simple equation in harmonic gauge. So then you see immediately the thing. This satisfies the same equation with sigma I, which is T0I over C. And you find that Gij is the opposite, the inverse of this thing times delta Ij. Okay. And why I'm saying this? Because if ever you have to work not with simply a binary system, but an n-body system, or a system in the solar system, where in the solar system you want to be able to describe the relativistic field not only in the middle of the solar system, but also on the Earth, because you have satellites around the Earth. So you want a coordinate system attached to the Earth. You want a coordinate system in the barycenter. You want the relativistic theory of transformation between various coordinate systems. And we have a series of papers with Sofer and Xu in which we show that this exponential parametrization is valid in all coordinate systems. And that so there is a W near the Earth, there is a W in the barycenter, and then there are linear everything becomes linear. Why usually if you expand this, you need nonlinear terms, W's. Just, okay, it was in passing. If you need a PN thing, then look at this exponential parametrization at our papers with Sofer and Xu. And also let me mention that we had used this with Blanchet for a long time, and then after this, so this was with Blanchet, and then Sofer and Xu. And then after this, more recently, Cole and Smolkin introduced a different way of understanding why the exponential parametrization is useful from a Karuta-Klein reduction, okay, which is just compatible and a nice viewpoint on this. Now, the next thing I want to talk about is gravitational cell force. Let me write here, so I don't need this equation. Gravitational cell force, GSF, or sometimes just cell force, it is the perturbation theory in which you consider a limit of the binary system where one of the masses, let's say M2, is very large, and M1 is small. Then you start from the probe limit. The probe limit says M1 really goes to 0, and therefore the space-time is a Schwarzschild space-time or curve if it is rotating generated by M2, and M1 follows a geodesic in this space-time. And then you can solve explicitly the scattering. So in this limit, which by the way is the limit where the symmetric mass ratio, remember this nu defined this way, when M1 is much smaller than M2, this becomes M1 divided by M2 and then tends to 0, okay? But it's a symmetric way of computing the mass ratio. So this is, so in the limit nu going to 0, this is the probe limit. You know everything. But the beauty of cell force theory is there is a 1 SF. So this would be called 0 SF. That is, you have the 0th approximation in cell force. The 1 SF corresponds to what in QFT would be called a one loop effect, which is saying we are going to take into account the fact that this small mass is also perturbing space-time. So G mu nu is G mu nu created by M2, and then there is a term proportional to M1, which is, let's say, H mu nu, which is the 1 SF thing created by this thing. So, which means at point X, I can solve this by using the Green's function in the black hole spacetime, but cell force computes more, so it means you can compute at infinity effects linked to this, but you can also compute the back effect of this on itself. This is why it's a one loop diagram, saying the cell force of a small particle acting on itself in a black hole background, which is complicated to compute because you don't have an explicit expression of the analyte of the Green's function. You expand it in multiples, you have an infinite series, you have divergences, you need to regularize that, but it's known how to do it. I just want to say that, and then it gives access to terms in first order in U, away from the probe limit, and this is very useful information. For instance, thanks to beautiful idea of Detweiler, we discovered that a quantity called the redshift Z along the world line, which formally is infinite, but you compute the 1SF part, regularize 1SF part of the redshift of this, contains gauge invariant information. Then it was understood by Le Tiec, others, Blanchet, that actually it has a very direct dynamical information, and in particular there is a formula saying that if you compute this by cell force theory, you immediately get the A potential of EUB theory, because in EUB theory, let me remind you, you describe a two-body system in terms of an effective metric, and in the limit where nu gets small, the important quantity is the A potential, which is the G00 of the effective metric. Okay? So, again, this thing, it's the gravitational. Yeah, yesterday there was a question. You see, the gravitational potential satisfying the Newton's Poisson equation comes in G00 always, okay, and also in the special metric. This, in EOB theory, this thing, by definition, reduces to where U is defined here. So here, U will be, it's not defined, okay? So let me define it. So nu is, I thought it was defined, is Gm over C square R, okay? Depending on the context, where M is the total mass. So in the limit when U equals 0, this should be the Schwarzschild metric, 1 minus 2 gm over r, so 1 minus 2u. And then, at the next order, you have a term which is 1 SF correction linear in nu and terms in mu square. Okay. When you do post-Newtonian theory, you keep all the powers of nu. You don't do an expansion in small u. But you do an expansion in small u, okay? Because it's the potential. In self-force theory, you don't know, or now there are 2 SF results, but they are quite difficult. I mean, this is difficult to use. At the 1 SF level, you can compute this thing both numerically and also in post-Newtonian expansion to very high order. I mean, with Donato, Bini, we had shown how to go to the 10th PN order, and then other people using the method we had used, MST from the work of the Japanese, pushed that to 20 PN order. So it means you can compute this function, which, as we have seen, was computed in PN theory. It starts at 2u cube. This was the 2 new u cube I had written yesterday. And then there is A4, U4, where A4 was 31 pi square over 32, okay, something. In post-Newtonian theory, you can compute the term up to A5, which is for Pn, but in self-force, you can compute this to extremely high order, and it gives information. Okay, information valid only for small nu, but still useful information about this function u. Okay, this function EOB potential directly computed from this. Now, to complete, so gravitational self-force, let's a method, a version of EFT theory. Nowadays, the word EFT appears in papers in gravity every day because it is a general way of thinking, saying when I have compact objects and I don't know in this context what is the structure of these compact objects, I can try to look at a theory which describes this object as essentially a point particle. So this was used, you know, from 1930. I mean, this was used very early on by Mathison. The first one to do that was Mathison, who said extended objects, I represent them as delta functions and derivative of delta function. Now, this is one version of EFT, but then each flavor of EFT is keeping a different way of computing things in some limits, so they are not all equivalent. In particular, one of the first version, which was called non-relativistic general relativity, which is a bit surprising, but there is a meaning. It says it uses PL theory at some level, but still keeps some GR. Introduced by Goldberger and Rothstein in 2006. At the beginning, when it appeared, I was not super impressed because they were just reproducing elementary things that had been known for a long time. But over the years, there were new ideas, new concepts that were much clearer in this. So it's a complementary thing. It's useful to have various points of view, you know, on how to solve the two-body problem. Let me just say that the basic of this method is when you have a binary system with two bodies like that, you why in MPM you solve this by saying either I am in the near zone, the wave zone, I do matching, I compute the metric everywhere with matching. Here it is more EFT-like and more lost in the technical details, but still very useful in some contexts. You write that the metric G mu of x, you don't decompose the metric by saying in this region or this region. You decompose the field by saying it is the sum of two types of fields which have different wavelength content. That this part of the field has varies on scale, which is comparable to the distance between the two bodies. So it means, let me write this, that di of h, sorry, it's the reverse. It's always a bit confusing. This contains the so-called potential gravitons, which means the derivative of this with respect to space is of the order of the distance between the two bodies, 1/r, or if you were in the scattering, the impact parameter, and the time derivative of this would contain a small factor v/c times the space derivative. So it is Pn-like, okay? So it's like the potential graviton is a new way of saying Pn approximation to the thing, but in this part you keep the possibly long wavelength effects, like tail effects, where you look at things that propagate over very large distances, okay, in space and time, and then you put them together in the action, and then you integrate out the potential gravitons and things like that. And for some questions, it gives a very useful new way of thinking about this. Okay. Let me continue the list of methods. Among the methods, so there is EOB, which, although by itself you say, but EOB, it's not a new approximation method, it uses this and this. But sometimes, by combining things, it looks like a very useful way of combining information in a new way that gives something new. And then there is numerical relativity, NR, which is a totally different subject, but which gives very useful information, both for the case of bound orbits, with merger and computing the waveform, and also now with scattering, okay? One can do numerical relativity with scattering. Actually, the first paper that compared analytical EOB information was done by us with the group of Luciano Rezzolla in 2014, where we said, let's do scattering, and then we compared two things, and now there are many more papers, in particular the recent work in collaboration with Piero Betegno that I will mention later. And now I go to scattering. Okay. Yes. So let me keep some space here. Scattering approaches to the two-body problem. So there are various flavors also of scattering approaches. Let me also mention that my own, the way I got in understanding that scattering approaches is probably a useful thing is when I heard a beautiful set of lectures in Parma by Gabriele Veneziano on his work of the high energy scattering of low modes of strings, let's say massless particles like the gravitons that scatter at ultra high energy, and that was the only thing at the time which existed at the two-loop level, and they could predict things, okay? And then I thought about it and how to use it in other parts of gravity and EOB. But first, let's clarify that there are either quantum or semi-quantum or classical approaches to scattering, which looks, when you look at the distance, look the same thing, but they differ by subtle conceptual things, which also have important technical consequences. Like, but first, let me remind you that when you have the quantum scattering of two charges, okay, if you do Feynman type relativistic scattering of two charged particles, let's say two electrons, E, or two scalar electrons, you have a diagram where you compute the amplitude, okay, of
two charged particles starting with momenta p1, p2, and then coming out with p prime 1, p prime 2, where p prime 1 is p1 plus q, and p prime 2 is p2, let's say, minus q. So the momentum transfer is q. Q is p prime 1 minus p1 is the deflection, okay, here. You have an expansion, and this expansion, you compute the amplitude as a function of p1, p2, and q, if you are in a regime where you don't emit, so you have conservation, p1 plus p2 equal p prime 1 plus p prime 2, that's why I put minus q here. The first term is alpha over q squared, okay? So the usual way to say this, Feynman diagram says when you explain things, you look at each coupling at each vertex, so you have a factor E here, okay? And therefore, when you have one exchange, you will have E squared, and therefore, the coupling that will appear is E squared, but as we know, the dimensionless version of E squared is the fine structure constant, E squared over h bar c, okay? And the leading order thing is alpha over q squared. Okay. But the point I want to note here is what is the analog of alpha for gravity? Okay. For gravity, this E square is the coefficient, or it could be, if I have E1 and E2, it would be, E1, E2, okay? Is the coefficient of the potential energy between the two things, okay? So in gravity, the gravitational analog would be either G m1, m2, but actually it's better to say it's G E1, E2, because, let's say in the center of mass, because E equal mc squared, and if the particles are relativistic, for instance, it's not the mass which counts. It's if I can have a massless particle, if it has energy E, what counts is the mass, okay? Except that I should probably put C2, C5 here, okay, to have the... So it is the dimensionless fine structure constant. But now, if we do the scattering of two black holes, okay, if you put the energy or the mass of two black holes, you find that this thing is 1 over 137, okay? So it is a small parameter, and you can expand. Quantum perturbation theory is an expansion in this, okay? Here, this is like 10 to the 80, okay? So you need to think, how can you use perturbation theory, which is an expansion in powers of alpha, when the expansion parameter is so large. And why is it so large? Because it is 1 over h bar. So the quantum expansion parameter is actually 1 over h bar, not h bar. It is the opposite of the classical limit, just to be aware, okay, of this. Because it poses some problems, okay? That when you compute in a quantum way, so for instance in gravity, you will compute diagrams like this, okay? And you have to think, okay, am I really computing the quantum amplitude in a regime which is totally non-quantum? How do I extract the classical part that I'm interested in? So there are various ways of doing it. I'm not saying that people who do that don't know what they are doing. They know very well what they are doing, but one has to be careful, you know. There is one universal way of doing things, which was the way which was used by Amati, Ciafaloni, and Veneziano for years, and used in particle physics for years, which is the econal approximation. Okay. The econal approach is essentially WKB, but WKB says that the action is that the phase, okay, first, when you compute the scattering amplitude, actually you compute an angle, a change of direction of a vector in Hilbert space. And essentially, you compute an angle which contains exponential of the action divided by h bar, okay? So this is the classical action, and at the end you compute different S, which is the S matrix, and essentially WKB says that the S matrix contains somewhere exponential I. This is just a general thing. Technically, what you do is, I mean, one way to do it, which is a bit subtle, is to say, if I start from the S matrix, yeah, now I have introduced S, maybe I should put I for the action so that I can keep S for the S matrix, okay. The S matrix is 1 plus, I mean, it's written in general form, you know. 1 means nothing happens. It means the two particles do not interact, so only delta function. The P stays P, the P prime stays P prime, okay, things like that. And T is the real scattering amplitude where things start deflecting, okay? This is function of P1, P2, and Q, okay? And actually, it becomes a function of SNT, the Mandelstam variables, but let me keep P1, P2, and Q. There is one way to, and then you would think, okay, it is this object that will exponentiate. But actually it's not true. It's not this object. You need to do a transformation to impact parameter space. So the good object, and even this is an ansatz. That is to say, actually, people know it is wrong at the third order, but it works at the, so it shows it's also a black art, which what you do is you start from the T amplitude, okay, and you do the following Fourier kind of transform. This will be a function, so P1 and P2 will involve S, the Mandelstam variable is minus P1 plus P2 square, okay. It's the total energy square incoming in the system, okay, S. And instead of using Q, okay, for instance, at lowest order, the thing is alpha for gravity is also, we will do the explicit computation, but this is alpha G over Q square, one graviton exchange, okay, with something that I will compute, but as a function of Q, it is 1 over Q square. You do a transform where you do a Fourier transform with respect to Q. And this Fourier transform is defined with some coefficients, E times P in the center of mass spread. And then the Fourier transform is with respect to Q. And let me just define this. So you do a Fourier transform, I Q times B. This Q is the momentum transfer, is the change of P of one body, okay, of the first body, let us say, of the T as a function of Q, okay? And then it is after doing this Fourier transform where a function of Q becomes a function of the impact parameter that you say that this Fourier transform is a coefficient which is 1 plus order h bar and exponential of I2 delta 0 over h bar. That is to say, you find that it exponentiates well as a function of the impact parameter, delta, traditionally with a 2, okay? So it defines the econal phase as a function of the impact parameter. And then once you have, this is what ACV computed at 2-loop order, and once you have this econal phase, for instance, you can compute the scattering angle as being essentially modulo a certain factor that I won't describe, the derivative of the econal phase with respect to B, okay, with some P here that we will see later how this P comes. But once you compute, so you do a quantum computation, you do this Fourier transform to impact parameter space, you check it exponentiate, and then from the exponent you can compute the classical scattering angle of two quantum particles, maybe at ultra high energy. Let me, yes, and let me say that there is, so there are 3 different ways of using quantum scattering theory. One is to do a full quantum thing and then try to extract by knowing where is the classical answer at the level of the Feynman computation. The other one is to say, no, let's be econal. I will prove it exponentiate after this, and then I compute delta. And another one that I want to mention because it is quite important.
Excuse me.
Yes?
Is S the scattering metric that is equal to e to the I2 delta?
So,
Or T in this case?
it is,
It's,
you need the one,
it's
because you see, in this thing,
Yes, yes.
um,
So it's like classical scattering theory. That would be the phase shift.
yes, it is in the limit, because another thing I will mention is in some limit you recognize there is a potential and that the dephasing in this potential exponentiates and then is linked to t, but in the exponent you have the 1 plus I deltas. That's why it corresponds
It's
to
the
this
scattering
one.
metric. That
It's
is
the
equal-
scattering matrix, which, yes.
All right, thank you.
And let me mention just briefly, without entering details, the name KMOC, that is KMOC stands for crossover, maybe, and O'Connell, but now most people call it KMOC. It's a different way of saying how from a quantum computation I will get a classical result. Okay. Because from a quantum point of view, you say, okay, I have S equal 1 plus T as a quantum object. But what is the S matrix doing? The S matrix is transforming an in state in an out state. It says, if I have an in state made, for instance, of two particles, P1, P2, the out state will be obtained by acting with S on this. Okay. And now, if I am interested in a quantity, a physical quantity, which has a classical limit, for instance, delta P mu. Okay. Delta P mu, classically, it is the value of the momentum of particle 1 in the out state minus the momentum of the particle 1 in the in state, in the classical in state and classical out state. But then you could say, but this means this is the quantum operator, let's say like Landau, let's put a hat, so P1 mu average in the out state minus the same quantum operator, but average in the in state. And I want this thing. But what is this? Out is this, okay? So this thing is in, I have 1 minus I t dagger, because now I'm replacing, so this thing, the bra, is in S dagger, okay? The dagger of S. So, which gives 1 minus IT, P1, mu as an operator, 1 plus IT from this, okay? In minus the 1 contribution. And therefore, this thing is, I'm saying this because for a very simple reason, it is the sum of two terms. It is I, P1 mu, T minus T dagger, how does it usually, the T dagger disappears here. Let me check. Yes, here the T dagger should disappear. Okay, for reasons that I don't see immediately. This is the in value of a commutator of P mu with T, but I have also the terms in T dagger T, okay, which gives T dagger P1 mu commuting with T, okay, in. The conclusion is, if you compute a quantum amplitude, a quantum scattering amplitude T, and you want to compute any classical quantity, you will have not only a part which is linear in the quantum scattering amplitude, but which itself is a nonlinear expansion, but there will be also terms bilinear, which people call the cut term, because in diagrammatic language, these things means you have, you have a term where you have two amplitudes and the fact that this is a T dagger T, okay, and if you introduce a set of intermediate states, it is like a diagram where you cut the propagators. Anyway, let me not. There is a term linear and a term bilinear in the amplitude, and then in principle this thing includes all effects, and but one needs to crucially to take it into account, because also, yes, last point, then I stop. When you have this expansion here, you see that in T, which is part of this, there will be terms delta over h bar, but terms also 1/2 delta square over h bar square, 1 over h bar cube. So actually you get inverse powers of h square, but still you want to know correction of this of the same order 1 over h bar. So when you use a quantum approach, what is delicate is you want terms at some fixed order in 1 over h bar, but there are terms which are worse in 1 over h bar, and you need to be sure you have computed them correctly. The econat says, I know this, so I can subtract them, then I can just, it was to give you a flavor that using quantum scattering approaches actually is more delicate than what it looked at the beginning. Okay, we stop here, and we start here.
Okay. Questions? I have a question.
Yes?
You described in the beginning that sometimes you have to eliminate terms, you do field redefinitions, you shift quadratic terms back into it. Could this be related to gauge fixing in the beginning? That you have done the wrong gauge fixing, maybe?
Not, there does not exist a gauge where Einstein's equations fully linearize. So it's not enough to say there exists a good field redefinition, although, for instance, this thing, which is a field redefinition, linearizes a lot of Einstein's equations. So, and when you compute nonlinear terms, they become linear in this after doing this. So the logarithm of the metric, in a sense, is better, but not always. For instance, there was in the previous lectures I mentioned the link with double copy that Einstein was the square of Young-Mills. People try to find good gauges where Einstein's nonlinear field equations, you see that they are the square of Young-Mills, and actually they could never find, okay? When you compute the S matrix, it is invariant under field redefinitions, so you don't worry about this, but when you compute things in the bulk, you need to work with some gauges.
Many questions.
Merci. I'm a bit confused about the scattering approach and the PM expansion. It seems to me that the scattering approach plus the classical limit is closely related to the PM expansion.
Yes, yes, yes.
Both
It is.
are
I will do, after the break, I will compute explicitly the 1 PM to see.
Yeah. And my question is the following. In PM expansion, I think that you solve the equation of motion by using the retarded Green function.
Mm-hmm.
Instead, in scattering approach plus the classical limit, you use the Feynman propagator.
Yes.
So how it's possible that maybe there is something in the classical limit? How it's possible that the solution is?
Yes. The answer, the precise answer to this, because you say, I checked the I epsilon, is K-Mock, okay? Although Dyson, you know that there are two versions of quantum field theory, okay? Schwinger had written actually a purely causal thing with nested commutators, okay? Which, and Weinberg has shown that this is precisely causal and equivalent to the retarded thing, okay? But Dyson, Stuckelberg and Dyson had understood that the causal Green's function, delta, with the I epsilon, actually encodes causality, and although when you compute the scattering amplitude, it is an in-out divided by in-out, so it is symmetric between the parts, it is still causal. And those terms, the things that I badly explained, but just to say this, actually you find that there are I epsilon here of Feynman here, I epsilon here, and these various I and no I here, they cancel the I epsilon of the other and re-establish the retarded nature. Okay, so it is subtle. Yes.
For the NRGEFT, what's the benefit compared to like PN and PM for solving a two-body problem? I didn't quite understand that.
So first, I should say that there are still discrepancies in the sense that some quantities computed by this disagree with other quantities, and therefore there is something that we don't fully understand. But some of the things where I could see they give a nice view, it's about these exchange diagrams. Like in multipolar post-Minkowskian, you have tail effects acting back on the system, and the way they are described in this thing is very simple, because there is the outside theory, where this thing couples to the multiple moments, and then you can write immediately the diagram for this and this. Except Forfines Touhani have done this, and others have done this, except that there are also mistakes in the literature. So it's conceptually it's nice. And the fact that there are terms that you can resum, that there are logarithm linked to tails and tails of tails, and this approach said, we understand this is a UV effects and infrared effects, and we can resum logs this way. Then they gave a formula which indeed resums interesting logs. Okay, so I still am slightly confused about what is the precise relation, but conceptually it's certainly useful.
I found some suggesting, I didn't know, the use of dimensional regularization in gravity. Now, I would like to have your comment on the fact that there is a possibility that quantum space-time has a dimension which is not actually 4, because of micro black holes or foams and something like that.
But then it would be a real dimension. I mean, it would be like a Hausdorff dimension. Or
yes. Here instead it's going into the...
You really need
this is more
dimension, you need analytic continuation. Okay, it's really technical.
Okay.
But it is true that when I started, for instance, my first works on this, because I was introducing point particles at a very high level, I knew there were infinities that were delicate, and I did everything with analytic regularization, where you analytically continue something else, so that I could understand mathematically in 4 dimensions what it means. When you are in 4 plus epsilon dimension, we don't know what we are doing, but we have experimentally shown in several cases that it gives the good answer. In all cases, I know.
So let's thank you both for the first part.